this one first. So if I start an LT Spice, so most of you guys have your laptop with you. If not, you know, we have LT Spice in the lab. You know, just open it up and start a new schematic and press F2. You'll find out this is way easier. Okay. Press F2, it brings up all these components. You can find a voltage. And F2 again, it can pick up a NMOS 4. Let me tell you why it has to be 4, because there are 4 terminals. So the fourth one in the middle is a substrate connector. So we are going to cover semiconductor physics starting today actually. That's my plan. And we'll do that for about 2 to 3 weeks to understand why we need a connector for the substrate. So the P substrate to avoid effect is called body effect. It's going to increase the threshold voltage of the NMOS or the PMOS. And we don't want that. So that's why we have to short all the body connectors of the NMOSes to the lowest potential in the circuit, which is ground, and short the body connector of the PMOS to the highest potential in the circuit, which is VDD. That's what we do. Just do it, then done. So these are the 2 components you can find from the library, and also PMOS 4 as well. That's a PMOS. And the difference between these 2 are, so the NMOS is pointing inside, but the PMOS, the arrow here is pointing outside. And so the person who designed this, or the company who designed this software, they didn't make this pin in the middle like what we draw on a paper. The reason they want to do that is they want to indicate that which is the drain, which is the source. A lot of times it doesn't matter, but here they just want to tell you like which is D, which is S, because when you are probing the current, it's going to show ID or IS at a different location. So the one closer to the gate pin is a drain. So for the PMOS here, so for the NMOS it's easier to understand. Oh, it's the source, sorry, it's the source. So the pin just beside that gate pin is a source. So that's the source. That's the drain. I forgot what is the source, what's the drain. So we'll cover that pretty soon. So current flow from the top to the bottom. So for the PMOS, I have to rotate it. Okay, grab it and rotate. I want to mirror it. Okay, and place on the top. Because we know that the PMOS here, that's the source, that's the drain, and we usually connect the source to the VDD, and that's the drain, that's the source, that's the NMOS. And if you just directly make a connection like this, you got an inverter, right? That's an inverter. Connect this one to a power source and ground it. And you right click it, can define the model name, the length and width here. And for example, I just put a 1U, 1 micron, 2 micron. It's not showing up. So the way you can do that is control right click and check this box to make it visible. So see the size of the transistor. And definitely you can change the name of it if you are using a different model file. The C5 underscore models.txt uses PMOS and NMOS. If you are using the model file from the textbook, it should be P underscore 1U or N underscore 1U. Like this. That doesn't matter. You can change it if you like. So of course you need a VDD here, you need a ground here, and the way you can connect everything to the power supply, you can just directly create a voltage node, right? I just name it as VDD, and I name this as VDD as well. And if I ground that one, so all the grounds are being shorted together, and all the same names of the voltage nodes are being shorted together. So this is directly shorted to here already. You don't have to connect them using the traces. And right click, for example, is 5 volts. And also let's do a simulation. I'm going to name this node as in and this as out. And I will ground this one, the body of the NMOS, and I will short, or I will just oh, so people like tutorials. So after I started making posting all these lectures to YouTube, the ones are usually just like 20 views or something, but the LT Spice tutorials like 5,000 views, and people are commenting as well, asking me questions from India, from all the other countries. So people like tutorials. I'm thinking if I keep making the same LT Spice tutorials, I can make money from YouTube. I need a model file, right? So I don't have a model file right now. Where can I get a model file? Probably here. Let's see. Oh, not here. Oh, here. C5. Where's C5? Is this C5? We didn't see C5. These are not. Okay, let's just use this one. So I also have to save this on the desktop. And this. So because if you open this model file, you can see that the name of the devices are N_1U or P_1U, right? So I have to change it to P_1U or N. So for the inverter, it's being powered up right now properly with 5 volts. And this is 1U, 1 micron, 2 micron. And I will just make them the same size, 1 micron, 2 micron, and control right click to make the size visible. And I can run a DC sweep. From 0 to 5. See if that works. No, it's not working because the DC sweep, they need a name of the first source of sweep. Did I make anything wrong here? What's wrong here? Oh, models. Dot include. What's the code for the DC sweep? Do I need a 0 here? Zero DC5. VDD has been added to here, so it's ready. I have a voltage source. Doesn't like electrical VLSI, you don't have a voltage source. I have a voltage source here. It's already powered up. So I'm sweeping that in.
I know, but I think you might actually
Oh, that's right. That's right. Thanks. No. So DC, when you're doing a DC sweep, the DC value here doesn't matter. I can just give a 0 to it because I'm sweeping this anyway, right? And I change this to in. I'm thinking that no, it's not case sensitive for RT5s because it's always a lowercase in showing up in the message. So let's take a look at the first lab. I'm just thinking if I need a ground in there. No, it's not here. I'll just add a ground. So it's going to be is that V in? Okay. Really? Or V2? Let's try it. Okay. And now I probe in, it's linear, and out. It's being inverted. So when it's being inverted, you can find out the switching point. So this is the output. I just probe it. Right? So here's the switching point. And look at the y-axis. It's 2.09 volts. Will trigger the change, right? So whenever the input is increasing, and there's at some point that whenever the input and output are the same values, it's called the switching point. Why the input and the output is the same value? Because there's an intersection here. So both input and output are at the same voltage at this point. But usually you prefer 2.5, right? How can I make it exactly at 2.5? So you need the switching point being shifted to the right. So which means you need a stronger NMOS. You need a stronger NMOS to pull it down to 0. So just make the NMOS wider. Let's see if that works. It's making things worse. Why? I just did it oppositely, right? Think about that. I'm getting a stronger NMOS. So it's stronger, it's actually pulling the volt output to the ground earlier. So when your input is not actually getting that high, but since you have a stronger NMOS, it's going to pull the output down to the ground earlier because it's stronger. That making sense? So actually you want to change it back to 2U and make your PMOS stronger. And then run it. Still not 2.5, but getting closer to it. 2.44. It's pretty good. That's how I designed this. So the reason for that is, so they have different threshold voltages and also different mobility for these, the holes and electrons. We'll cover that pretty soon. And so they have a different capability of opening up the channel according to the input. So that's why the PMOSes are usually weaker compared to the NMOSes. That's why you relatively need a wider PMOS in order to make the switching point right at the 50% of the entire voltage range. So switching at 2.5. So that's a quick example about how to use LT-Spice, and also you can create a symbol out of it, do the very similar job compared to electric VLSI. So we were talking about, so Kelvin just showed me the circuit. So what was the problem? Oh yeah. Oh yeah, so the pulse, exactly. So let's see another thing I want to show you guys. So, oh, did I? Then just doing electric. It's very similar. Either one. I mean, I'm showing you spices because it's relatively easier compared to electric. So you can directly grab a voltage source, and you couldn't do it over there. Exactly. So it has a better interface here, and the reason I wanted you guys to do it there because part of that design probably is being used for the lab, so you can directly use it for the lab. That's why I probably ask you guys to do it in electric VLSI. It's worth the effort. You have to do it anyway. I accept either one, whatever you want to use. It's fine. And so for the time, how do you change the time of the pulses? So it can be difficult to find out what are these parameters in electric VLSI in the SPICE code. But if you put a voltage source like this in here and do a transient analysis, go to advanced and go to pulse, and you'll see all these arguments. So it's V1, V2, delay, rise, fall, on, period, and number of cycles. So you can find out what are these arguments for this pulse function. The way to make the clock slower is just to make it slower here, and then you can copy and paste, or just look at this the locations arguments, and just make it slower. So for example, I'm not getting this into the nanoseconds level, right? So it's 0, 5, initially it's 0, but at the very beginning it's going to jump to 5 volts. And no delay, you can just put 0 there. And T-rise, you want a sharp rising edge or falling edge. So I just do, usually I do 10 pico. It's either one, doesn't matter. It doesn't have to be 10 pico. I mean, 1 nano is fine as well. T-on, so here's how you can make it slower. So whenever it rises to 5 volts, it's going to stay at 5 volts for a period of time. And you want to make it slower, so just make it longer time, so the clock is slower. If I do like 1 millisecond, so I can guarantee it's going to work. It's super slow. And periods will be 2 milliseconds. So the older version of LT-Spice won't allow you to do this because the rising edge and falling edges are taking time. So the period is not perfectly twice as much as a T-on to get a 50% duty cycle. So the newer version is able to tolerate with that. So you can directly just do a 1 millisecond and 2 milliseconds for the period. It works. And number of cycles, you don't have to specify that because it's going to run whatever it is able to run during that transient analysis time period, which is 1 millisecond. So that won't work because your T-on is already 1 milli and you just simulate for 1 milli, you won't see any pulses. So I just do 10 milli. So I can see like 5 periods in there. And all these are being inverted, right? And if you slow down the clock, probably you'll be able to see correct signals. But it's sometimes difficult to tell what are these arguments. And LT-SPICE can be a place to find out the solution. Any other questions? Anything? Would Friday help?
Yeah.
Friday works? Okay. Undergraduate is not easy. Actually, graduate school is easier compared to undergraduate. Don't have to take that many classes. And usually the professors are easy graders because they have to mentor graduate students and postdocs. They don't want to grade every single homework and become picky because it's getting more trouble for them. They have to argue for that. What's not right? Taking them more time. I'll just give you A. For graduate school, not undergraduate. Undergraduate is different. The reason undergraduates are not getting good grades in these large institutions because the professors usually do not teach. They ask a graduate student to teach. Every time is different. Depends on their personality. They ask their PhD students to teach full time, even though they are being paid only 20 hours a week. They can be very lazy or can be very outstanding. Depends on who we want to be. And they can be either because they're not being required to be a good teacher after they got tenure, which takes 6 years. So, when I was in graduate school, it's a big number of professors, not a single one. Quite a few. They won't even show up. You couldn't even see them in the office area. I mean, you are wondering, like, do they have office hours? Just couldn't find them. They show up and teach. After they got tenured, right? They show up and teach, and then they leave the college. They will just stay in the university for that, like 3 hours a week, and they have TAs to grade everything. They don't even need to grade. Sweet job, right? 3 hours a week, getting 6 digit in there, but you have to work pretty hard for the first, I would say, like 6 years. You don't want to be that kind of professor. You want to work with students and get funding, pay students, get internships. I feel bad if I become like that type of professor. I mean, I couldn't even look at my students through their eyes. I mean, I feel shameful for that. So that's probably why he just stayed on the college for 3 hours a week, so that he is not able to see other people's eyes. Camera is not working. Um, if I keep adjusting the camera for another 20 minutes, I'm done for today. It's an easy job as well. Camera is not working. Let's cover some semiconductor physics. So semiconductor materials can be silicon, can be germanium. What's the symbol of it? Ge. Can be gallium, arsenide. These different materials. The reason they are being called as semiconductor materials is because the conductivity of these materials is between the conductor and the insulator. So the conductors are, we know, metals, right? So like copper, that's a conductor. And insulator, for example, glass. So these are semiconductor materials because we can engineer these materials to make them, to control the conductivity of them. So they are controllable, doesn't like these ones. It's auto control, either nothing or superconductive. So the reason that these are superconductive is because they only have one, sometimes two valence electrons in the outer orbit of the atom. So for copper, how many protons it has? So copper is Cu, right? Have you learned it somewhere? Chemistry, a little bit chemistry in high school or somewhere? Is that Cu for copper? So that's a proton. How many? I couldn't remember as well. So it's 29. 29 protons is plus 29. So there will be, and there are 29 electrons exist as well. So they are being distributed as 2, 8, 18, and 1. So how many valence electrons it has? 1. So it is able to lose that electron easily. That's why it's a conductor, because it only has 1 out there. Will lose it easily. So the electrons can move around in between the atoms. For another one, for silicon, silicon has 14. So it's 2, 8. So these are the different orbits, right? And 4. So it's not 1 or 2. But it's also not like 18, right? So it's not too bad. So that's why it's a semiconductor. You are able to modify the material to make it conductive. It's not an insulator. Has 4 valence electrons. So silicon is the most common material being used in the semiconductors, but we have to dope it with different materials to control the conductivity of it for different purposes. And so these materials are called dopants, like phosphorus, spell that, and boron. These are the 2 most common dopants. So the way to dope it is you have a piece of silicon and you spin coat these materials, or you just place some of these materials on the top of the silicon and place that silicon with these dopants into the oven, usually a furnace. So at that certain temperature and pressure, these materials will diffuse into the silicon and mixed with the silicon atoms. For example, silicon has 4 valence electrons. And the way, because a piece of silicon has many silicon atoms in there, so all these atoms are combined by this covalent bonds, because every single atom has 4. So 1, 2, 3, 4. And at the same time, the neighboring silicon atom is gonna contribute another electron and to form this covalent bond. With that silicon. And you can imagine it's just repeating for every single atom. I just didn't draw them. If you dope phosphorus into this silicon material, because this has 15, I guess, 15 is 2, 8, and 5. So that one is going to contribute 5 electrons. So the way that it's being mixed with all the silicon material atoms is it's just replace one of the silicon atom in there, for example, for one atom, phosphorus atom, and it has a P in here, but 5 free electrons, like that. And then still have a lot of silicon atoms around it, but only 3 are able to form these covalent bonds, but this one has been occupied by this phosphorus electron. So there will be another electron out there, which is a free electron, to make this material more conductive compared to the original silicon material because of the extra electron. And this is called N-type semiconductor material. That's N-type. The reason it's called N-type is because, you know, N will remind you about the negative, right, or minus, or negatively charged, because you got one more free electron, so that's why it's negatively charged. So it's called the N-type material. And another dopant, the boron, boron has 5 protons, so it's going to be 2 and 3. And if this is being doped into the silicon material, originally it was a silicon in here. But after this is being doped into this material, it's going to replace that silicon atom in the middle and have a B here. But it only has 3 free electrons. And then the silicon atoms around it will contribute 1 to form that bond, 1 to form that bond, 1 to form that bond. And what's going to happen for this one? The silicon still has 1 electron here, but the boron doesn't have another one to form that bond. And so, we just created that concept, which is called a hole. Just a spot for an electron, but there's no a real hole in there. It's just called a hole, and it's positively charged. So in the boron doped silicon, it has more free holes. For phosphorus doped silicon, it has more free electrons. And this is called a p-type. And this has more free holes. And this is a p-type semiconductor. So if you dope it for a longer time, for example, you place everything in the furnace for a longer time, there will be more boron or phosphorus being diffused into the silicon, so have more dopants in there, and it has a higher conductivity, right? If you do it for shorter time, it's not that conductive compared to the longer one. And also you can control the concentration of the material you apply on the silicon with all the dopants. If the concentration is high, then they are going to diffuse faster into the silicon. And that's how you can control the conductivity of the materials. But before that, right, before we have the dopants, you couldn't do anything about it. The silicon has the same conductivity all the time. Metal as well. So that's a doped material, and there are some concepts for the terms. First one, for intrinsic semiconductor. So this Ni is the number of free electrons and holes in a unit volume of intrinsic silicon at a given temperature. Ni is the number of so intrinsic means it's not doped with any materials. It's just a piece of silicon. So P is a number of per unit volume, which is square centimeter. So in that volume, at a given temperature, that's the number of free electrons and holes. So this is a constant if the temperature is given, and it's a silicon material. It has to be silicon material. And in that volume, this number equals to 1.5 times 10 to the 10th per cubic centimeter, and this is pretty useful number because you have to use it for a few calculations. So let me give you some examples. And so first you know this constant, and also Np equals to Ni squared. It's another equation. This works for both intrinsic and extrinsic semiconductor materials. So this is a doped silicon. It won't be super accurate, but it works. We can use this equation to calculate the concentration of holes or electrons. And so after you dope that silicon with phosphorus, for example, so there will be a concept called concentration of donor atoms. Nd, concentration of donor atoms. N because it's a N type. D is a donor, right? So it's actually the concentration of the phosphorus if you are using phosphorus for that purpose. And ND because this is called a majority. So if you dope intrinsic silicon, just a pure silicon material, with that phosphorus, then the concentration of the donor concentration, the donor atom, is pretty much the same as the concentration of the electrons. Think about it. Why? So if I write it down like NN, so this N means it's an N type, and this N means it's an electron. So this is the concentration of the electrons in the N-type semiconductor. N-type is a silicon being doped by phosphorus, right? That's an N-type, has more free electrons. And now, if I dope it with that phosphorus, then it's considered as a donor, electron donor. So the uppercase N here means the concentration of the donor atoms. Concentration of donor atoms. So if I donate, for example, if I put 10 phosphorus atoms in there, I would say, because every phosphorus atom is going to contribute one free electron. Okay? Is that correct? And the number of atoms is going to equal to the number of free electrons in there. You want to say it's not, because silicon may have some free electrons there as well originally. I know it's boring, but let's get through this. You have a better understanding of what you are laying out in the circuit. So, because whenever it's doping that phosphorus into the silicon, there are just so many of them. Compared to the original number of electrons in the intrinsic silicon, this is way more than that. It's not in the same level. For example, in the intrinsic silicon, you have 1.5 times 10 to the 10th. Seems like there are a lot. But the thing is, whenever you dope it, it's not at the same level. It's going to be like 1.5 times 10 to the 14th, for example. I mean, let's not say 14th. Let's just say like 12th or 13th. It's still significantly larger than this one. So it's going to be like, so this is only contributing to that number 0.001. So when you're doing the calculation, you can ignore it. So the original silicon seems like this number is high, but actually it's not compared to the dopant. So whenever you are doping something to it, you got a spoon full of phosphorus, how many electrons do you have in there? And billions, I couldn't even count, right? So compared to this one, it's just so many. That's why I can directly say the donor atoms is the same number of the free electrons in there, because after this has been doped into the original silicon, this one dominates the number of free electrons. It's pretty much like how many atoms I have, how many free electrons I have in the final product. There weren't that many, only this many, right? So that's how you can directly use this equation. Is that clear? The same for the p-type. But let's do run some calculations. For this one, here's an example. So after is being doped. After the silicon is being doped, just wait, just cool it down and wait it for hours maybe, and there will be a state being reached. It's called equilibrium. Equilibrium is achieved. So whenever equilibrium is achieved, Pn equals to Ni square, and Pn equals to Ni square over Nd. So all these ones are from quantum mechanics being derived from there. And we just need to know how to use it. So Ni, remember, that's the intrinsic, that's how we can make the, can link this calculation to the intrinsic free electron concentration. So is a conclusion from the physics, right? So we have this number here already because it's a constant. We have a piece of silicon and it's being placed in a certain temperature, and then boom, we have this many electrons per cubic centimeter, right? That's the conclusion here. And if we dope it, if we dope that silicon with some materials, we can still use this number. Pn, so remember here is an N-type. The N-type semiconductor and the concentration of the holes. The N-type semiconductor and the concentration of the electrons. So if you use the N-type, the concentration of the electrons times the concentration of the holes, this equals to the square of the number of free electrons in the intrinsic semiconductor. Why? I don't know that exactly like quantitatively why I can derive this equation for you. I'm pretty sure it's not exactly equal to that. It's pretty close to that, but let's think about this intuitively. Why this is possible? So when you dope, so it's an N-type, right? So N-type means I doped that material with electron donors. Okay, so there will be a lot of electrons, and then there will be less holes because the electrons are filling into the holes. So that's why it is possibly to be equal to that number. I know this is boring. So on Wednesday, give you a boring topic. It's just getting things worse. There will be just some calculations on this. Won't get it, too deep into this topic. One homework assignment, one quiz probably. It's definitely not the main topic of this class, but you guys need to know the basics. We'll take 2 weeks to work on this one. So you just need to know that this works, and I can use that one to calculate for the concentration of the holes. Why? Because I can control the concentration of the electrons when I'm doping that material. I know the concentration already. So this, for example, you know this, and this Nn equals to Nd, right? So this, if you know this number and you plug into here, and this is constant, so you can calculate for the concentration of the holes. So how many holes are left in the material after I doped that? So here comes that equation. I'm glad I'm not a physics teacher. Oh my goodness. Look at your face. Poker face. All right, we're done for today, I guess. 2 minutes left, and we'll meet on Friday. Continue this topic. Oh, we should have a quiz, but we don't have time, so we won't do the quiz today. So let's do it on Friday though.